Okay, so if you want to see if your answer is right, go ahead and fast forward to the point where I've got the answers to both of these written out. Just fast forward to the end of the video. You can check it out. For this first example for the nearest neighbor method, it says after there's a complete weighted graph, which I've given you, select a starting point. So you get to start anywhere you want, okay? I'm going to start at vertex A because that's where most students decide they want to start whenever we do this problem. So I'm just going to start at vertex A. And again, I'm going to write down where it is I begin. And I'm going to follow the algorithm. So it says move to an unvisited vertex by traveling along the edge with the least weight, starting at my starting point, which is A. So looking at going to B, E, G, F, or C, my least weight is going to be at a cost of 11, whatever that happens to be. Then from point B, I have to choose the cheapest weight, no matter what it is, not going back to vertex A. So that's going to G at a cost of 13, or a distance of 13, or again, there's no context here, and that's okay. Then from there, my next cheapest option is to take this edge of weight 19 to F. And then from F, I can go to E for the cheapest, 15, 23, 41, 37. So I'm going to go up to E for a cost of 15, distance 15, again, however we want to think of it. And then from E, my cheapest, notice, is my 14, which goes back to A. But that's a problem because then I would create a circuit. I would have ended up back to some place I've already visited. I never would have gone to vertex C, however. So we're not going to be able to take that 14. In fact, regardless of what the cost is, the only place I can go next is to vertex C. It's the only thing I happen to be missing. Now, in this case, it does also fit the bill for the next cheapest. So now I'm at C at a cost of 17, and then we have to get back to where we started. And so regardless, I've been everywhere, and now we have to form the circuit. And so we end up at A with a 33. And then whenever you total all those up, we find that the total cost or time or distance, again, there's no units in this problem, would be 108. Now, if we do the same problem using the sorted edges method, okay, sorted edges says find the cheapest unused edge on the graph. It doesn't matter where it is, okay? So you look at all the numbers in the graph, that happens to be cheapest one going from A to B at 11. Okay, so A to B, 11, that's what we write down first. Then you look at everything else on the graph and you write down the next cheapest value, so long as you haven't created a circuit that doesn't include all the vertices and you don't end up with a vertex that you have highlighted that has degree 3. So the next cheapest is the 13 from B to G. B to G. For 13, okay? Then you look for the next cheapest of all the edges, and so that happens to be A to E, that 14 from A to E. And that is not breaking any of our rules either. We have not created a circuit, and we don't have any vertex with degree 3, so we're okay there. Then the next cheapest is going to be, let's see, the 15 from E to F. That's not creating a degree 3. Not A, E to F at a 15. Okay. Then the next cheapest edge is that 17. However, notice if we use this edge of 17, if we would use that one, that makes vertex E have degree 3, and we cannot do that. So we're not going to include the 17, okay? So if you want to like X it out so you know not to use it, it's just that your mind won't be drawn back to that number again, that's fine, okay? The next cheapest is the 19. We can't use that one either because that would create a circuit that doesn't include vertex C. So we can't use the 19, so I'm just going to cross it out so I don't look at it again. Let's see, my next cheapest is the 23 from B to F. And that's not going to work. That would create a circuit where I don't want one. Let's see, the next cheapest is the, looks like 25 from B to C. But if I include that one, notice I would have degree 3 at B. I don't want that, so we're going to get rid of that one. Next cheapest is 27. I can't use the 27. That would link up A and G and give A degree 3, so I can't use that one. Get that one out of there. My next cheapest is, let's see, the 33 from A to C. But notice if I go from A to C, A would have degree 3. I can't do that. So let's see here. Now I'm at 36 as my next cheapest. That works. G to C. G to C at 36 is my next best deal. That does not create a degree 3, and it gets me to a vertex I haven't visited yet. All right, and then we repeat. My next cheapest would be the 37 connecting C and F, and at this point I have visited all my vertices. That would complete my circuit, and it doesn't give me any vertex of degree 3. So C to F at 37, and whenever you add up that total, it's 126. So do notice in this case, the nearest neighbor method and the sorted edges method, they do give you two different answers. I said in the last video, it is not always the case that those two algorithms give you the same result. In this case, they don't. It's just a matter of which one you would want to use. Maybe the best solution, I don't know, is to do both and see if one gives you a better one in like a real life practical standpoint. Because again, clearly going through 120 options if you do the brute force method is probably not the best method of choice.